For a lunar habitat, we need a location with almost permanent sunlight. On most of the lunar surface, day and night each last 2 weeks. The axis of rotation of the Moon-Earth orbit is inclined only 1.5 degrees to the Sun. For this reason, at some peak points very close to the poles, sunlight is almost permanently available. We need sunlight that is as continuous as possible to generate electricity and to illuminate greenhouses, where oxygen and food are to be produced self-sufficiently. Additionally, the ability to mine ice is another good reason to build a habitat near the poles. There are permanently shadowed regions on the pole caps where the temperature never rises above 200 degrees Kelvin and water ice never could sublime in the vacuum.
Hello! Let me explain our lunar habitat and its components by using this 1:16 scale model. Above ground is a truss frame tower made of carbon fiber tubes. It is based on a circular magnetic rail and it rotates to follow the direction of the sunlight. The tower holds a reflective mirror membrane that reflects the horizontally arriving sunlight down into an artificial crater where a second cone-shaped mirror reflects it into a toroidal greenhouse. In order to pre-stress the mirror membrane into the desired shape, a second parallel membrane is provided and electrostatically charged. Thus, both membranes attract each other. The stronger the electrical voltage, the stronger is the curvature of the mirror membrane. This way, we can adjust the focal point. With the given area of the mirror, 65 kilowatt of sunlight enter the greenhouse. This results in a light intensity of 265 watt per square meter, which is the optimum for photosynthesis. To simulate night, the mirror simply can be turned away from the sun for 5 hours within a 24-hour cycle. The greenhouse structure consists of a prefabricated ultralight inflatable membrane covered by several meters of loose regolith. The combination of an inflatable structure covered by loose regolith and mirror membranes leads to a solution that features the lowest payload mass of all concepts. Additionally, it offers an excellent protection from micrometeorites and cosmic radiation and the use of natural sunlight for self-sufficient production of food and oxygen inside the greenhouse. Since this homogeneous transparent membrane material does not feature a very high tensile strength, it is reinforced by a diagonal net of Dyneema ropes. Other inflatable modules for sleeping compartments, connecting tunnel corridors and workspaces can be attached to the greenhouse torus and to each other to expand the habitat. Carbon fiber frames with sluice doors form the connection points for the added modules.
To reduce the stress on the inflatable membrane structure, we provide 500 millibar or half of atmospheric pressure only on the inside. This is equal to the air pressure on the peak of the Mont Blanc, the highest mountain of the Alps. We compensate the low air pressure with a higher oxygen content of 35%, which was the level on Earth during the Carboniferous period. But even at 500 millibar, the inner pressure is 50 kilonewtons, equal to 5,000 kilograms per square meter at Earth gravity. In comparison, the weight of the regolith deposit is almost negligible. At lunar gravity, a 4 meters high deposit of regolith only presses down with a force of approximately 11 kilonewton.
This makes structural 3D printed walls and ceilings obsolete, and we can significantly reduce the risk, the payload mass, and the energy requirement that are involved in the time-consuming 3D print process.
For 3D printing, we not only need to bring a 3D printer to the moon, but also magnesium oxide. In order to process lunar regolith into printable material, 1% of magnesium oxide must be added to the total mass. Even that 1% adds dozens of tons to the payload. The other point is the energy requirement for 3D prints. Unfortunately, there are no data published about the energy requirement of 3D print with lunar regolith. But we could find data for the production of rock wool that comes very close chemically and physically, since it consists of molten and formed silicate as well. According to these numbers, 6,000 kilowatt-hours of electricity are required to 3D print 1 cubic meter of regolith, or from 1 to 2 square meters of wall. Solar particle events come horizontally on the lunar poles, while galactic cosmic rays come from all directions in space. Galactic cosmic rays also produce secondary radiation when they hit the shielding material. With the first 50 gram per centimeter square of shielding, about 1/3 of the galactic cosmic rays are absorbed, which is by far not enough. It needs about 300 grams per centimeter square of shielding material to absorb the secondary radiation, and only from then on, with increasing mass, more radiation is shielded effectively. By covering most parts of our structure with 4.5 meters of loose regolith, we achieve a shielding of 800 grams per centimeter square. However, this diagram refers to a particle flux that hits the surface of the shielding material in a 90-degree angle, but in reality, the angle of incidence is quite random. Arriving in a flatter angle, a large portion of the radiation has to pass through more shielding material than the perpendicular flux. Thus, the effective dose which the crew receives is even lower. The artificial crater is a zone where cosmic radiation is not blocked and can reach the greenhouse, but it is only a fraction of the radiation that reaches the surface of the moon. Inside the greenhouse, the points closest to the window receive the most cosmic radiation. On open surface, radiation can come within a 180-degree cone from all directions. In our case, the cone limited by the crater rim shall not be wider than 45-degree angle average. That reduces the received radiation to 1/16 compared to an open surface. Humans would not spend much time at these most exposed points near the greenhouse window. At any other point deeper inside the greenhouse, the perceived cosmic radiation is much less. Taking into account the even more effective shielding of radiation arriving in flat angles, the average annual radiation dose can be kept under 25 millisievert inside the greenhouse and under 15 millisievert inside the sleeping compartments. This is well below the legal nuclear energy worker annual dose limit of 50 millisievert. For the selection of a suitable site, the following criteria have to be considered. A maximum of uninterrupted solar radiation for food production in greenhouses and for producing electric power by photovoltaic devices. The site should be in close vicinity to places where relevant amounts of water ice are supposed to exist. The vicinity of the habitat should be reachable by rovers. The site needs to consist of a flat area, large enough and in the right shape so that the habitat structure can be extended. We need a suitable landing site in a safety distance. It should be preferably on a lower altitude than the habitat itself, so that regolith particles cannot be flung onto the habitat by rocket thrust. Places that may fulfill these mentioned criteria have been identified and suggested in several studies. We finally chose the C1 area on the South Pole and the H0 area at the lunar North Pole as exemplary building sites for our habitat design. Each mirror casts shadows on the other mirrors. The more distance kept in between, the shorter the period of the shadow casting on others, while the moon rotates with regard to the sun within a 29 days synodic lunar cycle. The task was to find an arrangement where the mirrors cast as little shadow as possible on each other, and to keep the traffic ways short to avoid too much regolith being moved between the greenhouses. In any square grid or triangular grid array, there would be numerous shadows from many directions. Only in a one-dimensional linear array, shadows only come from two directions, regardless of how many mirrors are added. To use the land and tunnel system more efficiently, we will provide two parallel rows of mirrors in different heights. In our design, the mirror centers are chosen in a height of 10 meters and 20 meters, where mirrors in one row cannot cast shadows on the mirrors of the other row. The toroidal greenhouses are connected via modular tunnel corridors. Other modular rooms and facilities, as the kitchen, bedrooms, gym, laboratories, and workshops, are additionally connected. The traffic system is resilient. In case a tunnel module is seriously damaged, it can be bypassed by two other tunnel corridors. preparing the construction pit, the upper 30 centimeter layer of soil that is in contact with the membrane structure needs to be filled with smoothed out regolith. In order to provide a more convenient temperature environment for construction workers, machines and material, we span a very thin double-layered mylar membrane over the construction site. Sunlight is reflected into the construction space and infrared radiation is reflected back by the membrane. Smoothed out regolith is filled inside the greenhouse and it will be transformed into fertile soil. The excavators dump regolith in the fully inflated structure. The crew members can now work inside with normal air pressure. The truss parts for the mirror tower have been connected to an inflatable form and packed into a thin package. This package will now be inflated. With an inflatable form, we can pack the carbon tube structure into a small volume and quickly bring them into the correct geometry through inflation. Due to the inflated form, the carbon fiber tubes are brought into the correct geometric position and fixed at the crossing points. The lower truss ring with the magnetic rail and the upper oval truss ring that holds the mirror foil are assembled from modules and connected to the carbon fiber tubes. The truss frame tower is brought into the vertical position and carried up the artificial hill. The mass of the entire tower is approximately 400 kilograms. In lunar conditions, that is equivalent to 66 kilograms on Earth. The lower the gravity and the rougher the terrain, the more advantages legs have over wheels or even caterpillar drives. This legged vehicle can climb extremely steep slopes and can walk equally well in all directions. The cabin and shovel can rotate freely and operate in all directions. The greenhouses receive solar radiation from the mirrors. The total energy of sunlight received inside one greenhouse unit is 65 kilowatts. Finally, all of this 65 kilowatt radiation power is converted into heat when it is absorbed by the walls and the ground. In the lunar vacuum, the regolith around the greenhouse has a very low thermal conductivity. Therefore, the heat loss through the regolith cover is mostly negligible. The 65 kilowatt of heat need to be conducted away via cooling system. The cooling system consists of a convector inside and a radiator outside that radiates the heat into space. Between these two, we need a liquid circulating medium. This cooling system is very similar to that of the International Space Station. There is considerable heat loss when no sunlight is received during the short dark periods. During the dark phases, roller blinds temporarily cover the window. Dark phases can last up to 4 days at the C1 location on the South Pole and up to 11 days on the H0 location on the lunar North Pole. Even after 11 days, the greenhouse still can keep a temperature of 19 degrees Celsius, as our simulation with ComSol software shows. The toroidal greenhouses are the most important facilities within the habitat and they occupy most of the indoor volume. Here is where food, oxygen, and water are produced and recycled for the survival of the crew. Cosmic particle radiation is kept out while natural sunlight in a useful range from 320 to 2000 nanometer wavelength is reflected into the greenhouses via mirror membranes. In order to receive a radiation spectrum inside the greenhouse that is as identical as possible to that on the surface of the Earth, the mirror foil is made with a reflective silver coating. Unlike aluminum, silver reflects less UV radiation. But a small amount of UV radiation is important for humans to produce vitamin D and for the orientation of insects that can see UV light. It also is important for healthy plant growth. The radiation intensity is 265 watt per square meter in average. This results in a light intensity of 15,000 lux, the optimum for photosynthesis. On Earth, light intensity even reaches 100,000 lux at noon on a clear summer day, but this additional amount of light cannot be used for photosynthesis by most plants. Additionally, photosynthesis only works at the right temperature. It starts at around 5 degrees Celsius and raises with the temperature to a peak at 25 to 26 degrees for most plants. Under the optimal lighting conditions and temperature, each of these modular greenhouses can sustain 2 humans. An array of 16 greenhouses can form a habitat for 32 crew members. Inside the greenhouses, we can grow a variety of fruits, nuts, and vegetables for sustenance. Insects can be part of the ecosystem for pollination and recycling of organic waste. Their larvae can also supplement the diet for protein. Through photosynthesis, plants convert CO2 and water into carbohydrate and oxygen. Only photosynthesis in combination with composting of organic waste guarantees a 100% recycling of oxygen, hydrogen, and carbon. No machine can manage that so far. With the Sabatier process on the ISS with methane that cannot be used in the habitat, hydrogen and carbon are released into space. Since there is no carbon on the Moon, it is a big advantage when it can be fully recycled and does not need to be supplied from Earth permanently. Experiments already have proven that Moon regolith and Mars regolith can be upgraded to fertile soil when processed and enriched with the right additives. In one greenhouse unit, up to 500 liters of water vaporize daily from the plants and condense on the cooling radiators on the ceiling, from where the water is collected. Drinkable liquids can also be squeezed out of the fruits and leaves. On the ISS or any other space habitat without a natural greenhouse, water needs to be extracted and recycled from dehumidifying the air, filtering and distilling wastewater, and vaporizing water from excrements. This requires almost 1 kilowatt-hour per liter of water. Technical equipment and energy for recycling oxygen and water are not required here because it is done by living organisms. Other concepts usually include aeroponic food production in plastic shelves under purple LED light. But unlike natural soil, aeroponics do not include the composting of organic waste and depend on artificial nutrition solvent sprayed on the roots. The shelves, LED lamps, and watering system require extra payload. Plants need 250 watts of sunlight per meter square for optimum photosynthesis. The production of electricity through photovoltaic modules for LED light is by far not as efficient as natural sunlight reflected by mirrors. No short walk in a spacesuit through a barren radiation-polluted lunar landscape or shelves flooded with purple light can replace a walk in the forest. Spacious greenhouses with natural sunlight, lush vegetation, and biodiversity are not only a source of oxygen and food. Here, humans experience a natural environment full of sunlight where they smell different plants and hear the buzzing of insects.